Topic of this video, retrosynthetic analysis from Test 3. I had a student request that we do Fall 18 Test 3 Retro. Here's the target. Before we begin, let's look at what kind of reactions we're expected to know that put groups on benzene. Over here, I can guarantee that you will need these reactions on your test. You're going to need to know the nitration of benzene. You're going to do that several times on the test. Nitric acid, sulfuric acid, and heat. We'll put a nitro group on benzene. You are responsible for knowing many ways of reducing nitros to amines. This is one of them. If you want to see the other ones, go to section 22.3 of your book. Diazotization of the aniline will give the diazonium ion if you keep things cool. And then we learned there were 7 groups we could put on benzene using this method. I guarantee one of these groups will be on your target, as guaranteed previous semesters, and there we have a fluorine on there. That fluorine must be put on this way. I would like to point out that during this process of putting a fluorine on, although fluorine itself is an ortho-para director, and I don't see any groups in the target molecule where there are groups ortho or para to fluorine. Previous to having the fluorine on there, we had a meta-director called nitro. So if you can get the fluorine on there first, before you convert the nitro to a fluoro, then you can put your second and third groups on the meta positions. I think this is the approach I'm going to use on my retrosynthesis. I'm going to go to the nitro. I'm going to put another group on the benzene and go from there. So my last step in the forward synthesis, first step in the retro, will be conversion of the diazonium ion to the fluoride. Diazonium ion comes from an amino group on the benzene, which comes from a nitro group on the benzene. That is a meta-director. I see a primary alkyl group on both sides. This is a primary alkyl group. There's another primary alkyl group with some other functionality over here. When I see that kind of functionality with the O on an adjacent atom here, epoxides are coming to mind, but let's deal with that when we get there. Let's look at some more of our notes here, because there's a little bit of a bombshell here. We know how to put primary R groups on benzene, but we do not know how to do it directly. We must go first by way of a ketone or an aldehyde, in this case ketone. And that's a Friedel-Crafts acylation if you want to know. Just call it acylation. Acid halide, aluminum chloride. And then you reduce the carbonyl to a CH2. Carbonyl is now a CH2 using either the Wolff-Kishner on top or zinc amalgam and HCl on the bottom. With this new knowledge in mind, this primary group came from a carbonyl being here. Which came from an acid halide and the aromatic compound. We'll get to that later. As in previous syntheses, this is an ether over here, a Williamson ether synthesis. Can make that. Alkoxide reacts with primary benzylic bromide, also known as benzyl bromide, and that comes from benzyl alcohol, which we can circle. benzyl bromide comes from benzyl alcohol. This little gem over here comes from this molecule here, the conjugate acid. Now my strategy for getting that left portion onto benzene right here involves something I'm going to have to do some adjusting. If that was an organolithium, then I'd have a problem. This organolithium would react with itself. The C- here would find a second molecule's ketone and attack it. We can't have that. It's a classic case of a need for protection. This could be the nucleophile, and it could react with ethylene oxide to create this functionality right here. Ethylene oxide would be popped open by this nucleophile, and ethylene oxide comes from ethylene, which itself can be made by dehydration of ethanol. Circle that as well. Now the question is, where do organolithiums come from? Of course, they come from alkyl halides. Alkyl halide, if I have two metadirectors, remember, this used to be a ketone. That's a metadirector as well, this protected ketone here. So what I'm going to do is this. Here's the unprotected version. Both of these groups are metadirectors. The bromine has to go on meta to those two groups. The previous molecule will be this without the bromine, because the bromine's going to go where we need it with this approach. Now we have some flexibility, because if I put the nitro on first, then the next group goes meta, as pictured. If I put the carbonyl on first, then the next group goes meta, as pictured. So it doesn't really matter which group you choose to take off first. I'll choose this way, this piece, plus this piece with a chlorine on there. And then we're down to fixing things up. Spatially, I was running out of room, so I decided to go to the right here. This group, nitrobenzene, of course, comes from benzene, which gets a circle. And we got a little work to do still, but not a heck of a lot to get this molecule here. Acid halides come from carboxylic acids, which come from alcohols. This is one more carbon than benzyl alcohol. It would have been nice if it was benzyl alcohol, but it's not. So here we go. We have to extend benzyl alcohol by one carbon. One way we did on our first test was like this. An organolithium with formaldehyde will create a 2-carbon chain off the benzene. There's one carbon right there, second carbon here. This comes from methanol. Put a circle on it. There's a nice circle right there. And continuing this piece, this came from the bromo version. And we've already accounted for benzyl bromide previously. But, you know, we got a little room over here. Let's use it. And we got a circle on benzyl alcohol one more time. And I will put all the forward synthetic reagents on here, and we'll just zoom through that at the end. Before we run down the forward synthesis, maybe this box here has been bugging a lot of people. A little too much suspense for their liking. A little hint. I want you to look through the last 10 Test 3 Retrosynthetic analyses and find one that doesn't have a primary R group on the target. Yeah. I give this warning every semester, and I still see students try to directly put on a primary R group on benzene. They lose 1 point backwards, 1 point forwards. You can't do it. You try to do it, and there's a rearrangement. So, taking it from the top. Benzene. Nitric acid, sulfuric acid. We have nitrobenzene now. We're going to react it with this piece here, which we haven't made yet. So let's look at it. We have benzyl alcohol, PBr3 to benzyl bromide. Magnesium and diethyl ether gives benzyl magnesium bromide. Methanol reacted with PCC to give formaldehyde, which when mixed with benzyl magnesium bromide in the presence of HCl, in step 2, sorry, not in the presence of HCl. Step 2, add HCl. Gives this homobenzylic alcohol, which when oxidized with chromic acid in this form or the potassium dichromate form, gives this homobenzoic acid, which reacts with thionyl chloride and pyridine to give homobenzoyl chloride, which when reacted with nitrobenzene, a meta-director in the presence of a Lewis acid catalyst, aluminum chloride right here, gives this species right here. Bromination, given that there's 2 meta-directors here, must go on the meta position. And then protection of the ketone with ethylene glycol and sulfuric acid in the presence of a Dean-Stark trap for the condensation reaction gives this protected ketone, which can now be lithiated with lithium and hexane. And we have a phenyllithium species, which when mixed with chemical D, which we haven't made yet, better make D before you mix it with C. Ethanol dehydrated with sulfuric acid to give ethylene. Monomagnesium peroxyphthalate gives ethylene oxide, the epoxide. C and D can now be mixed, and then step 2, protonation to give the alcohol. Deprotonation, you could argue you could skip step 2 here and go straight to this here, and I would accept this argument. This is created by deprotonating the alcohol using KH to give this anion. Benzyl alcohol can be made into benzyl bromide by reacting with PBr3. We're going to mix these 2 species together with a nice polar aprotic solvent, DMF, to give this species here. Looks like I used a Clemenson to reduce the ketone all the way to a methylene, CH2. That is then reacted with hydrogen and nickel to give an aniline derivative here. Diazotization creates this species here. You have to keep it cool. I don't have the final step here. Oh heavens, I better put that in. Well, I'm having one of those days. I just did the whole forward synthesis without hitting record. Here we go again. I hope the element of suspense has not been driving you crazy about this box here. Here's a reminder I give students every semester. You won't find a retrosynthesis for test 3 that doesn't involve a primary R group on the target. Here is our primary R group. You have to go by way of a ketone first and then reduce it. Any other attempts at putting direct primary R groups on benzene end with failure and rearrangement to secondary or higher R groups. So, all I'm saying is you got to know this protocol, or else you're going to lose at least 2 points. Let's start with the boxes until they meet up with other molecules. Benzyl alcohol reacts with PBr3 to make benzyl bromide. It can then be converted to a Grignard reagent using magnesium and diethyl ether. Methanol can be reacted with PCC to make formaldehyde. We'll talk about A and B coming back later. Benzyl alcohol here, PBr3, we already studied that. Did it on the right side of the page. We're doing it again here. It is awaiting a molecule to react with. Benzene. Nitration of benzene using nitric acid, sulfuric acid creates nitrobenzene. It's awaiting for something to react with. This piece hasn't been made yet. So let's carry on this synthesis here now. We can mix formaldehyde B with benzyl magnesium bromide A, mix them, then add HCl to protonate the O and get an H. Chromic acid oxidation is achieved using chromium 6 oxide or potassium dichromate aqueous and sulfuric acid to create this carboxylic acid, which can be converted to an acid halide using thionyl chloride and pyridine, which can now react with our nitrobenzene as long as we have aluminum chloride catalyst to create this meta-substituted nitrobenzene. We can brominate because each of these groups is a meta-director and I want a bromine on the meta position. Bromination using bromine and iron, which creates iron 3 bromide catalyst to create this species. I'm going to protect the ketone of this species using ethylene glycol and sulfuric acid in the presence of a Dean-Stark trap, and I have this protected species here. Now I can lithiate that species using lithium and hexane to create this phenyl lithium derivative, which I'm going to mix with D. Did I make D? I can't remember. Let's just make D again. I don't think I did. Let's make D. Take ethanol, react sulfuric acid and heat to dehydrate it to make ethylene. Treat it with a peracid such as monomagnesium perphthalate to create ethylene oxide. That can react with this organolithium, followed by protonation in step 2 to create this alcohol. Then deprotonation of that alcohol using KH will create this alkoxide. If you want to go straight from C to this here, then just skip the HCl step. And I have no problem with you skipping this intermediate. Just in the lab, we always work reactions up. Anyway, a lot of talk about lab. We won't do that. We already made our benzyl bromide. It's going to undergo a Williamson ether synthesis. I wish I'd stop moving molecules around. Williamson ether synthesis by mixing and then adding a nice add a polar product solvent. Polar A product solvent first. I gotta slow down a little bit here. Add a polar A product solvent to a benzylic bromide and a strong nucleophile. You get this SN2 ether product, which then I reduced using the Clemenson, which gave me a CH2 on this position here, a methylene. Reduction of the nitro can be accomplished using hydrogen and nickel. Nitro becomes an aniline derivative. Diazotization is accomplished using sodium nitrite at 0 degrees Celsius in excess aqueous hydrochloric acid to create this aryl diazonium, which is converted to the final fluorine with a fluoboric acid and room temperature. I think I covered all the steps. I think we're finished this retro. I'm sorry if it ran a little long, but there you have it. Retros do take some time. I look forward to our next video.